Oh, very good. All right. Good morning, everyone, and welcome to the second lecture for this week for 124103 Biophysical Principles. Today, we will be learning about the kinematic equations. It's still related to what we've been learning so far, where we've been talking about how to describe the motion of an object. Um, but this time we will use kinematic equations to find one of the quantities, displacement, velocity, acceleration, or time. And so we'll do a little bit of problem solving, but we will also look at how we can rearrange the kinematic equations. And so I'll also give the mathematical background around how we rearrange equations. All right, so as I've mentioned earlier, so far we've been describing the motion of an object, and we've learned the definitions for distance, displacement, speed, velocity, and acceleration. And we need to know these four quantities in order to describe the motion of an object. We can obtain this using a velocity time graph. So looking at this graph, for example, the y-axis is the velocity in meters per second, and the x-axis is time. So if you wanted to find the velocity of the object, then we can just read the velocity from the graph. And if we wanted the time, we can also get the time from the x-axis of the graph. We learned last time that if you have a velocity versus time graph and you wanted to find the displacement of the object, then you get the area under the graph. And we said under the graph is actually the area between the graph and the horizontal axis. And if you wanted to find the acceleration given a velocity time graph, then we get the slope of that graph, and that will give us the acceleration. Right? So that's what we've been learning so far. But the graphical method may not have sufficient precision for an accurate answer. For example, we might have to estimate if we wanted to find, for example, the value of velocity at this point. Yeah, then we need to estimate, we're sort of estimating what's the value of the velocity here. So sometimes the graphical method might not be so accurate. So it will be better to use an equation called equation of motion to find displacement, time, velocity, or acceleration. And that's what we'll be learning today. These equations of motion are also sometimes called kinematic equations. All right. So kinematic equations, they're a set of equations that describe the motion of the object, and the equations relate the displacement, time, velocity, and acceleration with each other. So I've listed here the kinematic equations of motion. Again, you don't have to memorize these equations because everything will be open book, but it will be useful as we go along our lectures. It will be useful if you could sort of make a formula sheet, and as we go along, you're writing down equations or formulae, so that when you need them later on in the test or exam, you already have like this formula sheet of all the equations that we've been learning. So you don't have to memorize these, but it's important to know what each of the variables in the equations mean. So the variables in the equations, xi is initial position, xf is final position, and delta x, we learned if you have this delta, the Greek symbol delta, it means change. So delta x is the change in position, which we learned as displacement. Change in position xf minus xi, which we learned to be displacement. Sometimes you will see that x is only x is used. In this case, xi is assumed to be 0. So especially when you're looking at a problem and you sort of do not see a value for xi, you can assume that the starting point for the object is 0. It's at the origin, so you can say that xi is 0, and delta x is just xf, the final position. Vi is the initial velocity, vf the final velocity, a acceleration, and delta t the time interval. So also sometimes you just see t, and that's because we can assume ti to be 0, the starting time to be 0, and then the time for the motion will just be t or tf. Okay, so this lesson is just today's lesson will be looking at these kinematic equations and looking at how we'll use them to solve problems. So just a little bit of note here. These kinematic equations are only valid for constant acceleration, meaning a is the same all throughout the motion. But yeah, in this course, you sort of don't have to worry about that. We will only consider motion with constant acceleration. But I just wanted to point this out because these equations are only valid when the acceleration is constant. All right, so how do we use these equations to solve problems? It's really just pick and choose. So if you notice here, for each of the equations, they contain 4 of the 5 variables. So for example, the first equation contains VI, VF, A, and delta T, and it does not give any information about delta X, and so on. So the other equations also only contain 4 of the 5 variables. Right. So usually we use these equations. It will be useful to put up a table like this and list down what is given in the problem and say if delta X is not given in the problem and you want to find delta X, so obviously you cannot use equation 1. So yeah, we'll look at many examples and hopefully this idea will become clearer. But yeah, using these kinematic equations is usually just listing down what you know and then picking out from these equations what you can use based on what you know and what you want to find out. We will be looking at worded problems. Kinematic equations usually often involve worded problems. So it will be useful to know some of the keywords that could mean something when you're reading a worded problem. So for example, if you read in the problem that the object starts from rest, then that means that the initial velocity is 0. If you read in the problem that it says the object stops, then that means that the final velocity is 0. If the object falls vertically or is free falling, that means the acceleration is constant, equal to negative 9.8 meters per second squared. And we will learn that in the next lecture when we talk about free fall. But yeah, sometimes if you look at the problem, there will only be 1 or 2 numbers that will be given, but then you will read that the object starts from rest or that it stops, then you can actually pick out extra information from those keywords there. Right, so using the kinematic equations usually follows these three steps. It will be useful to write down what is given in the problem. These are the facts that you can pick out from the problem. And then based on the facts from what's given in the problem, you can pick which formula you will use and then use that formula to find what is being asked in the problem. Okay? So let's look at an example to see how we apply these 3 Fs. and the kinematic equations. So say a skier, okay, reaches the bottom of a slope. So let's say the skier came from the left. Yeah, skier came from the left, and then it reaches this point here at the bottom of this slope. He is traveling, the skier is traveling at 8 meters per second by the time the skier reaches this bottom of the slope. He then slides up another slope to the right and slows to a stop in 5 seconds. How far does the skier travel in this time when the skier started to go up this second slope and slow down because it's uphill? All right, so here let's write down again any worded problem. It's more convenient to write down what we know, what we're given in the problem. That those will be our facts. All right, so can we find what is delta x from the problem? Meaning, is delta x given in the problem? In fact, yeah, 5 seconds. Okay, 5 seconds is given. 5 seconds is a unit of time. So we're given the time 5 seconds. What else is given in the problem? Anything else? Any other quantity that's given in the problem? VI, very good. So we're given VI. The skier starts at 8 meters per second, and VF also very good because it says it slows to a stop. So we read the keyword stop there. So your VF is 0. Good. Right, so reading the problem, how far does the skier have to go? How far does the skier travel? That means delta x. That's what's being asked. And there's nothing about acceleration here. So we don't know acceleration. We only know VI, VF, and the time delta. So once you've written down your facts, then go to your formula, your kinematic equations. Okay, so let's say this is kinematic equation 1, 2, 3, 4, and 5. Which equation do you think can you use to solve for delta x? Is it equation 1, 2, 3, 4, or 5? Right, good. Okay, very good. So I'll see there in the chat box that you'll use equation 4. Yeah, any equation you don't know acceleration. That means any equation that contains acceleration cannot be used. And so all of the equations except for equation 4 contains acceleration. Therefore, you can use equation 4 to find what you want to find, which is delta x. So you go ahead and use equation 4 to find delta x. You have VF is 0 plus VI is 8 divided by 2 times the time 5. Okay, plugging all the numbers in the calculator, you should get 20 meters. Okay, does that sound okay? Did we get 20 meters in the calculator? Yeah, good. All right. Yeah, so that's essentially what I mean. Writing down the facts and then picking the formula based on what's given and then finding what's unknown. All right, now let's look at this second example. A swan gets airborne by flapping its wings and running on top of the water. The swan must reach a speed of 8 meters per second to take off and it accelerates from rest at an average rate of 0.40 meters per second squared. And we have two questions here. How long does it take to become airborne, and how far will it travel before becoming airborne? All right, so let's look at the fact. So let's do the first question. How long does it take to become airborne? Okay, so let's fill out this table of facts once again. So can you tell me anything, a quantity that's given in the problem? What do we know from the problem? Very good. Yeah, acceleration. Yeah, the word acceleration is not explicitly stated in the problem, but yeah, you're right, 0.4 meters per second squared. If you look at the units, you know that meters per second squared is the unit for acceleration. So even if the word acceleration is not explicitly stated, by looking at the units, you know that acceleration is given. What else is given in the problem? VF, yeah. VF, the swan must reach a speed of 8 meters per second. So we can say that that's the VF, 8.0 meters per second. Okay, do we know VI? Can we sort of, yeah, very good. Yeah, VI is 0. We can assume that the swan starts from rest. It starts flopping its wings before it can move. So VI is 0. How long does it take to become airborne? So that means delta T is what's being asked. And we are not given delta X. In fact, delta X is the second question. All right, so that's our table of facts. Now we go to the equations here. Right, so again, that's equation 1, 2, 3, 4, and 5. So which equation can we use to solve for delta T? Because we want to find delta T. Good, yeah? So I can see there we should use equation 1. Delta X is not known. We don't know delta X, so any equation that contains delta X cannot be used. The only equation that does not have delta X is equation 1. Right. But notice how in equation 1, delta T is here. It's sort of, it's tied up with acceleration. So we cannot directly calculate delta T using equation 1. Which means we need to rearrange the equation to find delta T, to isolate delta T and make delta T the subject so that we will be able to find delta T. Right. So before we can use equation 1, we need to rearrange it to isolate delta T, make delta T the subject, say delta T is equal to what? Right? So now let's learn how to rearrange this equation to isolate delta T. So before we talk about rearranging, I think the class has a varied background in terms of physics, and maybe some of you have done physics in school and you've learned how to rearrange. Some of you haven't been to school for a very long time. Some of you haven't encountered physics in school. So the method of rearranging that I will discuss in a minute is, I think, the most basic method. But if you've already learned how to rearrange and your method for rearranging works, you can stick with your method of rearranging. Yeah, I will present what I think is a basic method that hopefully beginners can follow. So the rearranging process is much like dressing and undressing feet. So when we put on our shoes, and we start from bare feet. If you want to put on stockings, we put the stockings first before putting on the shoes, right? It doesn't make sense to put the shoes first and then put put on the stockings, right? So when we dress up or we dress our feet, there's a sequence of what we need to put on first. Okay, and then when we undress, when we take off, we are undoing the putting on process, right? And then it follows an order too. The order of taking off is also important. It doesn't make sense to take off the stockings before taking off the shoes, right? Because it just won't work. So you need to take off the shoes first before you can take off the stockings, and then you're finally back to being bare feet. So with equations, rearranging equations, it's the same. We put on and we take off. But the question is, how do we know which one to put on or take off if we're looking at equations? Are we going to multiply something first? Are we going to divide it? Are we going to subtract or add something else? So what is the order of solving an equation? There's a rule called the order of operations, which we can follow to know which operation comes first in a mathematical equation. And that has an acronym of BEDMAS. BEDMAS. So the acronym BEDMAS, B stands for brackets and parentheses. So brackets will be the first priority. If you see brackets in the equation, that's what you have to calculate first. Next comes the exponents. That's a raised to the power of 2 or raised to the power of 3. D stands for division. That's the third priority. M for multiplication. It's also division and multiplication have equal priorities. Addition and then subtraction are the ones with the last fourth priority. Right, so if an equation involves 2 or more operations at the same level of priority, those operations are done from left to right. So, so this is the order of operations for solving an equation, BEDMAS. Let's look at an example to sort of just see what this all means. So for example, you're given this number, 8 divided by 2 times 4. Right? What is this equal to? 8 divided by 2 times 4. Is that equal to 16 or equal to 1? If you use your calculator pretty much follows the order of operations of BEDMAS. So if you use your calculator, you would get 16. Okay, if we work this out using our BEDMAS here, so you have division and multiplication. Multiplication and division, they're of the same order of priority. They're both on the third priority. And it says here, if an equation involves 2 or more operations at the same level of priority, then do the operation from left to right. So that means you have to divide by 2 first. 8 divided by 2, that is 4. And then you multiply that with 4, and that will be equal to 16. Right? Okay, it will be different if the equation is written as like this. 8 divided by bracket 2 times 4. What will be the answer to this? Is it equal to 16 or is it equal to 1? Yeah, good. All right, so because the equation is written differently and you have a bracket here, okay, the bracket is the first order of priority. Okay, that means you have to do what's in the bracket first you have to do 2 times 4 first. That's equal to 8. And then you do 8 divided by 8, which is equal to 1. Right? If you're using your calculator, then the calculator will be able to correctly solve this if you put the brackets, include the brackets in your calculator. So putting brackets when you're using your calculator can also be important. All right, good, cool. Right. So it's also important to know which pairs of operation do and undo something. Because we said, rearranging equations is like putting on stockings and shoes, but the order of putting them on and taking them off is important. So taking off will undo putting on. Similarly with equations, we need to know which pairs of operations will do and undo something. So we call these operations and its inverse operation. So addition and subtraction, they're inverses. Subtraction will undo addition. Multiplication and division. Division will undo multiplication and vice versa. And square root and exponent of 2. Right. So these are our operations and inverse operations. Right. So before we proceed to rearranging equations, is there any question about the order of operations or this slide here? Yeah. All right, so no question, I think. Okay, so now let's look at how we use BEDMAS and how we rearrange our equations. So this is what we wanted to rearrange to find delta t, right? VF equals VI plus A delta t. We want to isolate delta t by rearranging this equation. So first we need to put on shoes, right? So putting on shoes means building the equation up, starting from the variable that we want to isolate. So we want to isolate delta t, and we use BEDMAS to determine the order for which we will build this equation. Yep, very good. I can already see a correctly rearranged equation there, which is very good. Thumbs up, right? So let's start with delta t. Okay, that's what we want to isolate. Okay, how do we build this equation up? Starting from delta t. So we see that there's an A multiplied with delta t. So if we multiply delta t with A, we have A times delta t. So essentially, we've built up this part of the equation, A times delta t. Right. We multiplied with A first because BEDMAS says that multiplication comes before addition. Right. So that's why we multiplied delta t with A first. And then we add VI to have A delta t plus VI. But if you're adding two things, the order of addition is not important. So A delta t, sorry, I'm missing. A delta t plus VI is the same as VI plus A delta t. So essentially, we've already built up our equation, and that's equal to VF. So that's the putting on process. We've built our equation starting from the variable that we want to isolate. Then we take off the shoes. Taking off the shoes means that you undo the steps that you've done when putting on the shoes until you end up with a variable that you want to isolate. So to undo, you use the inverse operation, right? So you start from VF. Right? You start from where you've left off when putting on. So starting from VF, the last thing that you did was to add VI. Right? So you need to undo that adding by subtracting VI from VF. So now you have VF minus VI. Right? And then the next thing that the first thing that you did before adding VI was multiplying with A. So now you undo this multiplication with A. Okay, the inverse operation of multiplication is division. So that means you divide VF minus VI with A, right? And you have VF minus VI divided by A. And then you're back to delta T. So that means delta T is equal to VF minus VI divided by A, which is what Oksana wrote there in the chat. All right, is there any question about rearranging? Yeah, just watching the chat box. I don't see any comments in the chat box. All good, right? Yeah, if it's not clear, you can also private message me if you don't want the whole class to see your message, or you can speak directly on the chat and say it doesn't make sense, and then we can go over it again. But yeah, rearranging equations is one of the important skills. You'll find that you'll also need them even if in your biology courses. You'll also need to rearrange equations. So it's one of those skills that I would say would be important moving forward in your chosen degrees. But yeah, there will be a lot of opportunity for practice for practicing rearranging equations. Right, so let's move on. Okay, so let's go back to our problem with the swan. We wanted to find delta t, and so we now had this rearranging of delta t. Okay. Delta t equals VF minus VI over A. VF is 8, the table of facts that we've filled out earlier. The initial velocity is 0 and the acceleration is 0.4, giving you delta t of 20 seconds. Right? That's about 20 seconds. Well, good. All right, so it's just a matter of substituting numbers there. Now let's go to the second question. How far will the swan travel before becoming airborne? Again, we fill out our table of facts. We already know from previously VI, VF, and A. We have now the added information of time from the previous question that asked us to solve for the time. And we are being asked to find delta x, or how far. Right, we now have more options for which equation to use because we have this added information of delta t. Right, so if you want a rather straightforward, okay, let me just number this so we have some references. So yeah, which equation, if it were you solving this problem, which equation would you use to solve for delta x? Yeah, right. So equation 4, looking at equation 4, because we now have this extra information for delta t, we can use equation 4 directly, because then you don't have to rearrange the equation. And you can just directly substitute the numbers here and get delta x. Delta x is equal to VF 8 plus VI is 0 divided by 2 times 20. and that will give you 80 meters, right? Yeah. So you can use equation 4. It's simpler. You don't have to rearrange. It would still give you the correct answer. But if you wanted to, if you wanted to check your answer, or if you wanted to make sure, like if you weren't sure of your delta t answer, then you can use an alternative equation that doesn't use delta t, just in case, if you're not sure whether delta t equals 20 seconds is correct, because that's something that you've solved. You can also use another equation. What other equation can you use, assuming that you don't want to use delta t because you're not sure about your answer for delta t? Yeah, equation 3. Okay, so you can use equation 3 because it's the only equation that does not contain delta t. But then if you use equation 3, you will need to rearrange it to isolate delta x. Okay, so let's try. So this is equation 3. If you were to use equation 3, you need to rearrange that to isolate delta x. Right, so let's rearrange this equation to isolate delta x. Again, let's try to build the equation starting from what we want to isolate. We want to isolate delta x. So we start with delta x and we look at this equation. Delta x is multiplied with 2a. So to build up the equation, I need to multiply delta x with 2a. Right? Then I have 2a delta x. I've now built up this part of the equation, 2a delta x. And then you have this plus vi squared. So that means I need to add vi squared plus vi squared. Right? So if I added vi squared to 2a delta x, I would have vi squared plus 2a delta x. Comparing what I've built, I've actually now built vi squared plus 2a delta x, and that's equal to vf squared. So this is equal to vf squared. Right? So you've built up your equation. Now you have to do the reverse operation. So starting from vf squared, you undo the last thing that you did in building up your equation. So the last thing you did was to add vi squared here. That's the last thing that you did, add vi squared. So that means you have to do the reverse operation and subtract vi squared. So you therefore have vf squared minus vi squared. All right. Okay, and then you undo the multiplication with 2a. The reverse of multiplication is division. So you therefore have to divide with 2a. So you now have vf squared minus vi squared divided by 2a. And after dividing with 2a, you're now back to delta x. So therefore, delta x is equal to vf squared minus vi squared over 2a. All right. Good. Are we happy with this rearranging for delta x? Yeah. All right. Cool. I can see some thumbs up there. So let's solve now for delta x. Vf was 8 meters per second squared. So that's 8 squared minus vi was 0. 0 squared, it's still 0 anyway, divided by 2 times 0 0.440. You would still get the same 80 meters for delta x. If you're not getting 80 meters here, maybe try in your calculator, try to put brackets below this 2 times 0.4. So then you're doing 8 squared divided by the whole thing, 2 times 0.4. All right, any question about this rearranging or this problem, or are we happy? Are we all good? All right, okay. All right. Yeah, I don't see any questions in the chat box. I see some thumbs up. So let's move to this final example. A car is traveling at 28 meters per second. It's about 100 kilometers per hour. When a truck stops suddenly in front, if the maximum deceleration provided by the brake is 8 meters per second squared, how far does the car travel in the process of stopping? All right, so let's fill out this table of facts. What do we know from the problem? So can anyone give me something we can pick out from the worded problem, given quantity or variable? Yeah, right. We are traveling at 28 meters per second. That is VI. Right, and then what else? We are stopping, so our final velocity is 0. Okay, right, so we slammed on the brake. We slammed on the brake. When we slam on the brake, we will slow down, right? So in the process of stopping, we're slowing down. And that's actually what deceleration means. You're slowing down. And when you're slowing down, the acceleration will be negative, because then your final speed is smaller compared to your initial speed. Yeah, so yeah, you're right below. The acceleration here should be negative 8 meters per second squared. Okay? Deceleration means negative acceleration. That's when you're slowing down to a stop. Right, so be careful there. That's why I wanted to look at this example here to point out that if you're slowing down or if you're decelerating, you should include the negative sign in your acceleration. Right. And we're not given how long it takes for us to stop. And we are being asked how far, meaning what is delta x. Right, so which equation should we use? So obviously equation 1, 2, 3, 4, and 5. Right, obviously we are not given delta t, so equations 1, 2, 4, and 5 are useless, and we can only use equation 3. And we already rearranged that, so we don't have to rearrange that again. We already rearranged equation 3 earlier to isolate delta x, and this was the rearranging earlier. Vf squared minus vi squared over 2a. So let's just now go ahead and substitute. Vf is 0 because we're stopping. Vi is 28. Don't forget there's a square there, divided by 2 times 8. So again, you're decelerating, so you need to include the negative sign in your acceleration so that your delta x will be positive 49 meters. Right? Okay. All right. So yeah, some thumbs up there. Right, so that's essentially kinematic equations and how we use them to solve forwarded problems. Remember your three F's: facts, formula, and find. And then just rearranging equations would probably be the skill that needs to be practiced here. So with the remaining time that we have about 30 minutes left. Try to rearrange the following equations. So say in the first equation, VF equals VI plus A delta T. You want to isolate A, rearrange the equation so that you have A equals blah, 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 blah. Okay, and so on. So try rearranging these equations, and maybe we'll look at uh, some of the rearranging later on. But first, I want you to try rearranging these equations by yourselves first, right? Okay, maybe we can look at some of the rearranging. Yeah, yeah. Okay, so maybe let's try to do the first one. We want to isolate A. We'll build the equation up starting from A. We multiply that with delta t, because looking at this equation here, you have A times delta t. So you have A delta t after multiplying A with delta t. And then you add VI to that plus VI, and you have VI plus A delta t. That brings you to the equation for VF, right? VF is equal to VI plus A delta t. So you've built that equation up. Now undo the operations starting from VF. The last operation you did was to add VI, so you have to subtract VI. That will give you VF minus VI. Okay? And then you multiplied with delta t earlier, so you have to divide VF minus VI by delta t. So you have VF minus VI divided by delta t, and you're back to A. So therefore, A is equal to VF minus VI over delta t. So very similar method to what we did earlier to isolate delta t. Now for the second equation, we want to isolate delta t. Delta t is multiplied with this whole bracketed thing, VF bracket VF plus VI over 2 is multiplied with delta t, right? So to build this equation up, you have to multiply delta t with this whole bracket thing, right? And you can just multiply with the whole thing, bracket VF plus VI over 2. And that immediately builds the equation VF plus VI over 2 times delta t, right? And that is equal to delta x. So that when you do the reverse operation, starting from delta x, there's only one thing you need to undo, because to build up the equation, you only had to multiply with the whole bracket VF plus VI over 2. So there's only one operation you need to undo. So that's dividing with VF plus VI over 2. So therefore, delta x divided by the whole VF plus VI divided by 2 will give you delta t. So delta t is equal to delta x divided by VF plus VI over 2. Right? Okay, so hopefully that's not too confusing. If you look at this, maybe you're confused. There's a lot of variables, VF plus VI over 2, but you can just consider that as a single number or a single variable that's multiplied all together with delta t. And that's why you only had to do this single operation, multiplication operation, to build the equation up, and to do the reverse operation of division to to, to take off to tear down the equation, right? So the next example, next question is VF squared equals VI squared plus 2A delta x, and you want to find VI. Okay, so VI is here. You have VI squared, but actually what you want is only VI, not VI squared. And then VI squared is added to 2A delta x. So remember BEDMAS. Okay. So you build the equation up from the variable you want to isolate, VI. But looking at this equation, you have vi squared and then plus 2a delta x. Says that the exponent square comes first before the addition a. So that means before adding 2a delta x, you have to square vi first. You have to square vi first. So you have vi squared, okay, before you add 2a delta x. Right? So you have, therefore, vi squared plus 2a delta x. So you can add the whole 2a delta x, because even if it contains three variables, you can think of it as a single number that's added to vi squared. And you can see now you've built your equation up. Vi squared plus 2a delta x is equal to vf squared. Okay, and then you go back and undo the operations. Starting from vf squared, the last thing you did was to add 2a delta x. So you subtract 2a delta x from vf squared. You have vf squared minus 2a delta x. Okay, and then undo the square. What's the reverse operation for squaring or exponent of 2? Yeah, square root. So the inverse operation of a square is a square root. So that means you need to take the square root of this vf squared minus 2a delta x. Square root of vf squared minus 2a delta x. And then once you get the square root, you're now back to vi, because you've undone all the operations that you need. So therefore, vi is equal to square root of vf squared minus 2a delta x. Right? Right? Okay, the next one, now you have 1/2 a delta t squared and vi a delta. This is the longest kinematic equation. So let's rearrange this to isolate a. Right? So a is multiplied. A is tied up with 1/2 and delta t squared via a multiplication operation. So you have 1/2 times a times delta t squared, right? So multiplication comes before addition. So we need to build up this part of the equation 1/2 a delta t squared first by multiplying 1/2 delta t squared. Okay, when you're multiplying numbers, it doesn't matter the order of multiplication, right? So 1/2 a delta t squared is the same as a times 1/2 delta t squared. But essentially, we have here a times 1/2 delta t squared. Oh, that's times. It will be 1/2 a delta t squared, right? So you've built up this part of the equation here. Starting from a, you multiply that with 1/2 delta t squared, giving you 1/2 a delta t squared. Then you can add this bit vi delta t. So plus vi delta t, and you have vi delta t plus 1/2 a delta t squared. And that builds the equation for delta x. Okay. So going back, starting from delta x, you need to undo the last operation that you did, which is plus vi delta t. You have to subtract minus vi delta t, subtract that from delta x. So you have delta x minus vi delta t. Right? Undo the first operation that you did. The first operation was times 1/2 delta t squared. Inverse of that is division. So that should be divided by 1/2 delta t squared. That means you have to divide delta x minus vi delta t, divide that with 1/2 delta t squared. So delta x minus vi delta t, divide that by 1/2 delta t squared. Once you've done the division, you're now back to a, the variable that you want to isolate. So therefore, a is equal to delta x minus vi delta t divided by 1/2 delta t squared, right? Cool. Very long equation, but if you're methodical and just following, the putting on of shoes and taking off of shoes method, yeah, hopefully it will not be too bad. Okay. All right, and then the last one, we want to isolate VF. VF is tied up with delta t via multiplication symbol. So to build up this equation, we need to do the multiplication first before doing the subtraction. So we start with VF. We multiply that with delta t to have VF delta t. And then we subtract 1/2 a delta t squared. So you have VF delta t minus 1/2 a delta t squared. Yeah, and that builds up the equation for delta x. Doing the reverse operation, you start from delta x, undo your last operation, the last operation you did. Reverse of plus is minus is plus, so you need to add 1/2 a delta t squared to delta x. That will give you delta x plus 1/2 a delta t squared. And then you have to undo this times delta t by doing a divided by delta t to this previous equation here. So therefore, you have delta x plus 1/2 a delta t squared divided by delta t. And you're back to VF, which is what we want to isolate. So VF is equal to delta x plus 1/2 a delta t squared divided by delta t. All right. Cool. Any question about what we've learned in the lecture, rearranging equations and the kinematic equations? Right. Okay. Yeah. So essentially, that's what our lesson was about. We can jump right immediately to the workshop, and we'll do the same thing as well. I'll give you some time to look at the workshop worksheet. So it's already on stream. If you don't have a copy of it, you can download that, but it's this one, Kinematic Equations. It's this workshop here, rearranging equations and then some worded problems. In the rearranging of equations one, in the second question, it says rearrange this equation doing it in two ways. But yeah, you just rearrange it. You don't have to do it in two ways. Just rearrange it to isolate delta x. And you can use the method that we did to rearrange that. So it says here because it says here rearrange it using two ways. First, by dividing by 2a first, and by moving vi across. So you don't have to do that. The important thing here is to rearrange this equation to isolate delta x. And then we have worded problems here. The speeds are given in kilometers per hour. We haven't learned conversion yet. We'll learn that in the next lecture. So keep an eye on the chat box. I'll type down the conversions of kilometers per hour to meters per second, just for this workshop, because we haven't yet. Next time we'll learn about converting kilometers per hour to meters per second. All right. So maybe I'll give you until 11:30ish. Yeah, around 11:30. Maybe. Yeah, how about 11:30? We'll start. I'll discuss the solutions. Let's look at the solutions for the workshop problems. So from now until 11:30, I'll give you time to work on the workshop problems. And then at 11:30, we'll look at the solutions. Does that sound good? Are you happy with that plan? Yep. All right. Okay. I can see some thumbs up there. All right. Cool. Okay. I'll stop the recording.